So far in section 11.4, we've been talking about infinite series and their partial sums. And in these videos, I want to talk about what happens when your infinite series is adding up the terms of a geometric sequence. So let's remember our geometric sequence. Here's our explicit formula for a geometric sequence. So just as an example, we could have the sequence where a1 is equal to 3 and our common ratio is equal to 2. So let's remember what this does for the sequence. If I kind of write out a few terms, this would tell us to do 3 times 2 to the 1 minus 1, 3 times 2 to the 0. Next one would be 3 times 2. We'd be plugging in 2. We would get 2 minus 1, 3 times 2 to the first. And as we increase our n value, that's just going to increase the exponent on the 2 each time. All right, and we put that dot, dot, dot because this is an infinite sequence, meaning we keep listing the terms forever once we get the point. So for this one, these would be the numbers. Let's see, 3 times 2 to the 0, 3 times 1. 3 times 2 is 6. 3 times 2 squared, 3 times 4 would be 12. And then the next one would be 24. And remember, the hallmark of a geometric sequence is that the consecutive terms are multiplied by that common ratio. All right, so if we take these terms like this and we add them up in an infinite series, we get a geometric series. So for our example, we would have our sum k equals 1 to infinity, 3 times 2 to the k minus 1. And that would mean that we're adding all of these numbers up. So we'd be adding up 3 plus 6 plus 12 plus 24. Like I said, we could do plus 48. These go on getting bigger and bigger and bigger forever and ever and ever. All right, and then we talked about partial sums. So you could find the partial sum of a geometric series. So my partial sum, let's pick like the fourth partial sum. So we use that capital S, and then we put in the subscript our n where we're stopping at. So we're going to stop off at the fourth term in this series. So we would say 3 plus 6 plus 12 plus 24, and then no dot, dot, dot. We're going to stop there because it's a partial sum. We stop at the fourth term. And if we add those all up together, we should get 45. All right, so I'm going to show you a shortcut formula for the partial sum of a geometric series, and we're going to double check it with this one to make sure we get 45 using the formula as well. Here's our shortcut formula for the partial sum of a geometric series. So this is telling you that if you stop your infinite sum at some point n, so whatever our n was in our example, that was the fourth partial sum, so n was equal to 4, that meant that you stopped up here at that value of n. Instead of going all the way to infinity at the top of the series, you're just going to a finite number. And it says that it's going to be equal to a sub 1, that's the a sub 1 from the formula. And then the r shows up twice in the formula. That's that common ratio. And then that n is whatever partial sum you're on up there. So I just wanted to check our partial sum. So when we did 3 plus 6 plus 12 plus 24, and we got 45. So that was the partial sum. We went from k equals 1 to 4, and our formula was 3 times 2 to the k minus 1. So all I want to do is plug into this formula and make sure it gives us 45 just to spot check that it works. All right, so I've got a sub 1, that's going to be my 3. Then 1 minus our common ratio r, which for us is 2. And our n, our partial sum was the fourth partial sum. So we're going to plug in a 4 in that exponent. And then in the bottom, we're going to have 1 minus that common ratio, 1 minus 2. And then we can just simplify a little bit. You could use the calculator, but this one's not so bad. 2 to the fourth is 16. So I've got 1 minus 16, and 1 minus 2 in the bottom gives us a negative 1. So up top, I've got negative 15 in the parentheses. So we'll have 3 times negative 15 over negative 1. So those negative signs are going to cancel out, and I just get 3 times 15, which is 45. Now, if you're doing the fourth partial sum, this was probably a bit more work than just adding up 3 plus 6 plus 12 plus 24. But if I asked you to calculate the 100th partial sum or the 1000th partial sum, you would definitely want to make use of the shortcut formula. Let's try our formula on a partial sum we don't already know the answer to. We're asked to find the 11th partial sum of this infinite geometric series. And it actually doesn't tell us that it's geometric. Let's just spot check that that's actually true. So we want to check to see if each successive term has that common ratio, like what am I multiplying by to get from each number to the next? And it may be obvious to you, If it's not, you can always kind of reverse engineer this by division. So I can look at -4 and divide it by 8 to see what I must have multiplied 8 by to get to -4. And that reduces to a -1/2. So that's our common ratio. And we'll just check to make sure this makes sense. So -1/2, I would get -4. If I multiplied that by -1/2, I would get +2. Multiply that by -1/2, you get -1. So this does look like a geometric series. And if we wanted to do this brute force and just literally find the partial sum by adding up 11 things, we would have to go and create a few more terms, like 7 more terms to get 11 out of this series. But let's use the shortcut formula instead. So let's write this in our summation notation. All right, so this is going to be the 11th partial sum. So we're going to say k equals 1 to 11. We need a sub 1, that's our first term in the series. That's going to be our 8. Our common ratio goes in the parentheses, which was -1/2. And then for our geometric series, we always have this -1 in the exponent. All right, so let's plug that into our formula. The formula down in the box in the bottom right says I want a sub 1 in the numerator, so I want 8. And then 1 minus r to the n. So I need that r, that -1/2. So we need it in parentheses, -1/2 to the 11th, all divided by 1 minus a -1/2. All right. This one, -1/2 to the 11th doesn't look like a whole lot of fun to do by hand. So it is okay to use your calculator on these if you want to. I'm going to do this in a couple of steps so that you're able to check on your calculator to make sure you're getting the right answer. And if you're not, you can do some intermediate steps to figure out where you went wrong. So I'm going to figure out that 1 minus -1/2 to the 11th. So I'm going to do 1 minus -1/2 to the 11th power. And I get a bunch of decimals. So I'm not going to write them all out here, but I get 1.000488 and a few more. I'm going to keep that number in my calculator so I can keep all the decimal places. In the bottom, I've got 1 minus a -1/2. That's 1 plus a half. So you can have 1.5 or 3/2 down in the bottom. All right, so let's figure out what that's equal to. So I have 8 times that big long decimal divided by 3/2 or by 1.5. And I get a decimal, 5.335. Let's round that off to 336. Next number is 9. All right. And I'm okay with a decimal answer. You might be able to get your calculator to give you a fraction if you have like a decimal to fraction conversion button. Let's see what that would be equal to. Yeah, my calculator gives me an interesting fraction. It's 683 divided by 128. You don't need to give me the fraction. You can just give me the 5.336. Let's do one more of these. We'll be able to use the shortcut formula on this because we can recognize it as a geometric partial sum. Can you recognize it's geometric because it follows that format? The a sub 1 is the 6. Then you've got that common ratio, 3 in this case, to the k minus 1. That is a geometric series format. So because this series stops at 5, this is the 5th partial sum. And we know we can use that shortcut formula from the box. And it says to take a sub 1, so 6. In the parentheses, I do 1 minus r to the n. So 1 minus my ratio is 3. So 1 minus 3 to the n, which is 5 in this case. And then on the bottom, we'll do 1 minus 3. And again, you can type this in wholesale into your calculator. I'll do a couple of steps. I do 1 minus 3 to the 5th power. So I get -242 in the parentheses. And then 1 minus 3 is a -2. So let's type all that into the calculator. So 6 times -242 divided by -2, and I get 726. In the next video, I'm going to take this shortcut formula and see what it tells us about actually adding up an infinite list of numbers.